Okay, so let's get started. So, welcome to this sixth class on electromagnetic theory. And in the last few classes, we had discussed about electrostatics and magnetostatics. We spoke about Gauss's law, Ampere's law, okay, how they're analogous to each other, and then we had, we also talked about, how to solve for Laplace equations using the separation variables, basically how to find voltages, like potential differences, and from there find electric fields. And then also saw about how to do the same for magnetic fields, like if you have a current carrying wire, if there are steady currents that can result in magnetic fields. So how can one measure magnetic field? So we did discuss about all that and what are the typical relations, how the symmetry comes into effect there. And gradually we are building upon the Maxwell's equations, which lies at the heart of electromagnetic theory. So that's what we have been doing. Now, one important point was that we don't study nowadays. We don't like here. We are not studying. There's a reason why we are studying electricity and magnetism, like them together. Okay, and that's because they are very much related to each other. And today we will be mostly concentrating on how this relation came up. Okay, so basically, what is the relation between electric fields and magnetic fields and how they are connected to each other? Okay, and that connection and how does it come up in the Maxwell's equations and how does it govern? Basically, that lies at the heart of why we are studying electricity and magnetism together. So that's about today's things. Now, to start with, let's start with electromotive force. Okay. So consider you have a bulb here, so the bulb glows. Now, for the bulb to glow, there has to be a current that is flowing through it. So when you have normally you switch on and then you measure the current. So you know that anywhere in this wire, right, the current is expected to be the same, like all throughout the wire. But the point is that why is it so, right? Like from a very like if we say that you are starting the current here, so there has to be a flow of charge from one terminal to the other. So why don't we expect that there'll be charge accumulation at one end, and basically at a certain instant of time there'll be more charges maybe somewhere here and less charges somewhere here. Why is that not the case, right? So basically what happens is that the moment you switch on the circuit, there's this constant current that is flowing through the circuit, and in a way what we can say is that there is no such charge accumulation because that equilibrates, and that equilibration or the reaching of the equilibrium happens very fast, okay, within split second. So why is it very fast is a question, but the point is now if we first look at the case at like that transient phase where things have not equilibrated yet. So in that case, imagine a condition where there is current flowing, so there'll be like charges, maybe more charges flowing here than here at a certain instant. We are still at the transient phase where the current is not equilibrated throughout the circuit. So that means at any point, at a given point, there's I input and there's I output, and they are not equal to each other. Okay. So when that is the case, what would that lead to? That would basically lead to a charge accumulation, right? If I input is more than I output, you would have some, charge accumulation like this at this end. Now, if you look closely, what is this telling you? So if you have such charge accumulation, this will result in an electric field, which is in a direction opposite to the direction of flow of current, right? So this field opposes the current that is flowing in the you can say in the wire. So in a way, that is the reason this self-correcting field that you have is the reason which keeps the current uniform. Okay, and it happens in like very uh, small time period. That's why normally when we actually connect to a circuit, we basically get a constant current coming up. Okay. So now what we can say is that what is the charges moving in this wire experiencing? They would have some force which is coming from the source. So if you have force coming because of the presence of the source, and then you would also have some uh, force because of this electric field that is generated. Like I'm talking about the case where like basically in the equilibrium condition force, but to basically it's fine, right? I don't know about the network. Okay, so basically, there are two forces that are acting. So one is from the source, which we term it as Fs. So this you can tell as a force per unit charge. Okay, and then you have this electrostatic force, which comes because of this field. So you can say that F is equal to Fs plus E, and these are the two forces that are contributing. So now if you want to find the amount of work done as the charge moves from one point to another along this wire, you basically have to do the line integral, right? And if you have a closed circuit like this, you have to do a closed loop integral, like a closed integral over the entire loop. So this is why, because for the electrostatic field, we know that E dot dl goes to 0. So what matters is this. So basically, you have a source which results in a current, and this force Fs which comes from the source does a work which is as the charge moves from all along this circuit, and this is the work done. So this is what we call as the electromotive force. So in a way, this is not force. Okay, so this is work done by the source. Okay, and this is given by this line integral. Now, for an ideal source where you have, like a resistance-less battery, suppose, the net force should go to 0. So in a way, E should be equal to minus Fs. And if you put in here, this is what basically you get. Okay. So that means this is the definition of the potential difference. So if you have two terminals, A and B, suppose here it's A, here is B, what is the potential difference between the two is given by this relation here, right? It's the work done as the charge moves from one point of the circuit to another. That is what, so charge done per unit charge. Okay. So the work done per unit charge. So that is your EMF. Okay. Now, why are we discussing about it? It will be clearer as we proceed in the class today. This is the definition of EMF. Now, let us now talk about so what is happening still a net or it's not that network. Okay. So if you have a region where there is a net magnetic field, okay, and then you have this loop, okay, a closed loop, a wire, basically a circuit, and there's some resistor here. Now, what was seen is that you can have anything, basically a closed circuit. and then there's this region of magnetic field. Now, an interesting experiment was performed, and it was seen that when you move this loop with some velocity v, okay, and as it was moved, it was seen that there was a current that was getting generated in the circuit. Okay, so current meaning there will be some current flow, which means that there is a potential difference, right? Basically, an EMF gets generated. So this EMF was considered to be coming from the fact that you have this moving, this loop moving. So what was seen is that if you have this, closed loop, okay, some conductor, and then you are moving it at some velocity v, and here you have a net magnetic field. So effectively, what you have is moving charges in magnetic field, right? And we know that moving charges in magnetic field experiences a force, which is given by the, Q into V cross P. So force per unit charge will be given as V cross P, right? This is what we get. So if you now consider, so as you are moving, so all the charge along this wire has a net velocity. Basically, there is a net velocity in this direction. So all the charges are moving in this direction. Okay. And then you also have a magnetic field. Suppose it's into the plane or something. Okay. So which is perpendicular. So you can have something like a magnetic field into the plane or something. So you have a magnetic field, you have a velocity which is perpendicular to each other. So that means you have a net which this moving charge in this conducting wire would experience. Okay. So some notification. True. Yeah. So basically what we see is that, where is my point? So basically what we see is that when we have this loop moving, you have the charges moving with velocity v in this direction. There is a net magnetic field. So this region has a magnetic field. We are talking about motional EMF. Okay. So basically what we see is that we have moving charges because the loop, as the loop moves, this is a conducting wire. So the charges move with some velocity and you have a net magnetic field here. So moving charges in magnetic field experiences a force, which is given as Q into V cross P. So the direction of the force would be somewhere along this line, this wire, right? So now what you can say is that what is the work done by this force? Okay. So basically, because of this force, what would happen is you can imagine that whatever charges was there along this section AB, okay, they will try to redistribute. Okay, so there'll be a EMF or a potential difference between this terminals. Okay, between here. Similarly, when we are moving it, you can also try to find the forces along BC or AD, and because they're in the same direction, they're perpendicular, so the work done does not contribute. So what contributes is only the force along this segment AB. Okay, so you end up getting the force or the work done by this force as the charges get redistributed along this section. And that is given by nothing but, so if you want to find per unit, like the work done per unit charge, which is the EMF, it would be V cross B. And because they're perpendicular to each other, here you have VB. And then the charge can move from A to B, which is given as H. So the net EMF turns out to be VBH. Okay. So basically this EMF is coming because of the fact that you are moving this loop inside from a region of magnetic field. Now, there's another way of looking into it. So as you are moving this loop, in this direction with some velocity v, you're also changing the flux that is linked to this loop. Why? Because this is the region where your magnetic field is. There is no magnetic field here. So as you take the loop outside in this direction v, the flux changes. And how does the flux change? So if the magnetic field is given as B, we can find the flux as B dot dA. Okay. And for a rectangular loop like this, you can take small segments. And because you're moving with velocity v in this direction, so if you take this direction as x, basically phi is bhx. This is h. This is x. So bhx. And as you move the loop, this x changes. So the flux changes by this value. So now if you compare the rate of change of flux with the definition of EMF that we have initially discussed, we see that they're related, right? And it's nothing but this. So basically, minus of d phi dt, which is the rate of change of flux, is actually the EMF that gets generated in this closed loop. Okay. Now it's important to know that here, when you are writing this expression, it might, you might think that we know that magnetic forces do no work. Why? Because magnetic forces are always perpendicular to the direction of the velocity. So here the net velocity is in this direction. So the magnetic force is perpendicular to it. So why are we anyways trying to find the work done by the magnetic force? So basically this work is not done by the magnetic force. Okay, the magnetic force is only there, it redirects. So when you are moving this, you are doing some work, and that is redirected into a that results in the EMF, and we're trying to find that work done. Okay, so a potential difference, electric potential difference, that is getting generated along this region because of this external work that you are doing. Okay, so it's not in the truest sense the work done by the magnetic force. Okay, this will also be clear as we talk about the other examples. Okay, where you would see that even when there is no magnetic field in a region, okay, but the change of flux in a way can result in, net motion of charges, or net electric fields can get generated. Okay, so now based on this, we can try to solve this question. So here you can see a square loop of wire with side A, okay, at a distance S from the wire. And then you have a current flowing along the wire given as I. So it is asked, what is the flux of B through the loop? So for this question, the first thing that you have to say is that you want to find flux. So basically you want to find how the magnetic field lines cross this region. For that, you have to find the magnetic field that is generated by this current carrying wire. You have a current carrying wire, and we know the expression of the, we have done it, solved for it using Ampere's law, as well as, starting this, we did it with Biot-Savart's law as well as Ampere's law. So we basically know what is the field due to this current carrying wire at a distance S, also at a distance S plus A. So we know the field in this region, right? So because we know the field, now we can actually do a surface integral over this region, which is given by this square, to find the net flux, right? So basically this. So we know that the field for a long wire is given as mu naught I by 2 pi s, where s is the distance from the wire. And now you have to find the flux, which is given as P dot dA, basically a surface integral of the field in this region. So you can take small sections in this square loop, okay, with ds element. Basically, what you are doing is you are taking this ignore the spike. Basically, take a small section, okay, of ds element, and the other dimension is a. So this section has a dimension, has an area of a into ds. Okay, and then you do an integration from s to s plus a. So this is what is being done here. Flux. So this is the flux through the loop. So in order to find flux, you have to be like, you have to get used to solving for surface integrals, where you have to take in small such segments and then do the integration depending on what your dimensions are basically. Okay, simple question, finding the flux through the loop. So now the question says that if someone now pulls the loop directly away from the wire at some speed v, what EMF is generated? So basically what is happening is, you have this wire, there's a magnetic flux linked to this loop. Now you take the loop away from the wire. Now we know that as we go away from the wire, the magnetic fields drop, right? It goes as 1 by s. So that means the flux decreases. So because the flux decreases, there is expected to that is expected to generate a net EMF in the loop, right? And that would be nothing but minus d phi dt. Okay. So basically, if you know the speed with which you are taking the loop away, you know the rate in which the flux is changing, right? And that will give you the EMF. So basically, EMF is minus of d phi dt. Now, phi is given by this relation here. Now here, as you can see, you have this term, this ln s plus a by a, this has s here. And when you take the loop away, your s changes, right, so with time. So basically, you have to do a time derivative of this term, where ds dt is given by the velocity with which you take the loop away. Okay. So if you do that, this is the relation that you end up getting, right? So just doing a time derivative of phi. Phi is given by this relation, time derivative of phi, putting in the value of v equal to ds dt, you end up getting this term. So this is your EMF that is generated in the loop as you take the loop away from the current carrying wire, right? Now, what will be the direction of the, direction of the EMF that would be generated, or what is the direction of the current flow basically? Okay. So how to find that? So you can see that, there'll be some magnetic field here. You can consider, so if you have a current carrying loop, you can consider that the magnetic field comes out of the page, right? Just consider your thumb rule. You know that the magnetic field points towards you, right? But basically out of the page. And then you are taking the loop in this direction. So basically your velocity would be, so for this section, 1 second. So for this section, you would have a net velocity in this direction because you're taking the loop away. So this is your direction of V, and then your magnetic field is pointing outward, out of the page. So that already gives you the direction of the force, okay, which points towards this direction. So now this is your direction of force. Again, for this, you would again have a net direction of force in the other way. So that tells you what is the net direction of current that is flowing. Okay. Oh, sorry. One thing I had said wrong, basically. So you have a loop. Okay. Now here the velocity is in this direction. The magnetic field is pointing outward. Okay. So B is outward. So the field direction is along the loop. That is correct. Here also the field direction will be towards right. But the magnetic field here along this side, this side is actually lower than what you have here, right? So this would dominate. So basically the net flow will be in this direction, that is counterclockwise. Okay. Now one can also think of it in a different way, which is from this negative sign that you see here. So the EMF is, this minus sign tells us that the EMF that gets generated is in direction opposite to how the flux changes. So basically, as you go away from your current carrying wire, your flux is decreasing. So that means your magnetic field, the electric current should be in such a way, in such a direction that the flux increases. So when you have a current carrying wire, your magnetic field is pointing out of the page. Now for the square loop, you should have a current which also creates the magnetic field out of the loop, so that it tries to nullify the effect of decreasing flux, right? So that is what happens here. So again, if you have a, now if you consider the current carrying loop, the current has to flow in the counterclockwise direction so that the magnetic field points out of the page. Okay, so that also explains why you have a current, counterclockwise current. The next section says that what if the loop was pulled in this direction? So if it is moving in this direction, you can imagine the magnetic field is only dependent on S, which is the perpendicular direction distance from the wire. It does not depend on how, it does not depend on this direction, right? The magnetic field only drops in this direction. So that means if you move your loop along suppose X, along this direction, the flux does not change. And because the flux does not change, we can say that there is no EMF that gets generated. So because the flux is constant in this case, the EMF goes to 0. Okay. So this led to all this, interesting experiments that was reported by Faraday in around 1831. And this series of experiments basically brought in this connection between electric fields and magnetic fields. Okay. So the first experiment is something which we already discussed just now, which is you have a region of magnetic field and you take this closed loop. Sorry, ignore the spike. So you have this region of magnetic field, you take the loop along V, like move it as so that the flux linked to the loop changes, and we saw that there is a current that flows in this wire where the EMF is related to the rate of change of flux by this relation. So this is something we just discussed. What was seen is that you can also do another thing where you keep your loop intact, like there's no motion of the loop, but you change or move the magnetic field region in the opposite direction like this. Okay, so now this region of magnetic field changes. So this can be experimentally tried by taking the magnet away while you keep the loop at the same place. So what was seen is that even in this case, there was a current that was generated, and in the same direction it was generated, right? Now, what's interesting in this point is that, see here, you are changing or you are taking the magnet away, or the magnetic region is changed, but basically you don't have any charge moving, right? There's no moving charge. In the last case, when you moved this loop, there was moving charges and you had magnetic field. So you said that there's a force that the charges experience because of the magnetic field. But in this case, there's no moving charge. There are stationary charges here because you're not moving the loop. You are just changing the region of magnetic field. So the magnetic flux do change. So this again hints at the fact that the magnetic flux has something to do with the current that gets generated and not just the motion of the conductor. Okay. Another thing was, another such experiment was even more interesting, where what happened is you kept both of the magnet or the magnetic region and the loop, both were spatially at the same point, all were stationary, but the magnetic field amplitude was changed. It was a changing magnetic field. And it was seen that even in that case, there was a net current that got generated. So in all these cases, okay, what we see is that the motion of the conductor does not matter. Okay, the motion of the magnet does not matter. What matters basically is the change of flux. Okay, so now how do we explain that? Okay, why is this change of magnetic flux resulting in a in a net force on the charges? We know that stationary charges experience no magnetic force, right? Magnetic forces on the charges only come in when you have a moving charge. So now if the charges are constant, like stationary, why are they experiencing any force? So that led to the thought that maybe when the flux is changing, there is when there is a magnetic flux change, there is a electric field that is getting generated, and it is that electric field which is resulting in this potential difference or this current. Okay, so that led to this idea that a changing magnetic field induces an electric field. Okay, and it is that electric field that you see here, and that results in the motion of the charge along this loop, conducting loop. Okay, otherwise, just the presence of magnetic field for a stationary charge should not cause any force for them to move in this loop, right? No current should be generated. So it's the electric field that is getting generated because of the changing magnetic field that is causing the current to occur. So now if we use the definition of our EMF, which is given by this relation, and we know that this is related to the rate of change of flux by this relation that we just derived from the motional EMF. So what you can rewrite is, you can rewrite this phi as B dot dA, basically writing it in terms of the surface integral. And then you can also use the Stokes theorem to change this line integral to a surface integral. So that gives you a relation between curl of E and the changing magnetic field. So in the case of electrostatics, we did see that curl of E went to 0. Okay, and that would typically be the case for the situation if your magnetic field is not there or if it is a constant, right? So that means in the electrostatics, where there is only electric field, there this term goes to 0, and so curl of E is 0. So it's consistent with the result that we had initially derived in the electrostatic case. But here, because if you have a changing magnetic field, this changing magnetic field would result in an electric field, and the electric field will then be related by this relation. Okay. So now you can see that there is a relation which is relating the electric field to magnetic field. Okay. So that's how gradually this two fields, which were initially considered to be, separate events, are gradually turned out to be very much connected to each other. Okay. So based on our discussion, we can try to solve questions like this. So a conductor of certain length moves at right angle to a uniform field flux density. So the magnetic field strength is given, and the velocity of the motion of the conductor is also given. So what is the induced EMF in the conductor? So this is something which we just discussed. Okay, so it's just numerical based on the question of motional EMF, the topic of motional EMF we just discussed. So the answer would be this. So let's see how. So basically you have this conductor moving with some velocity v. Velocity is given, the length of the conductor is given, and the magnetic field strength is given. So now as you move, we know that the induced EMF is given by this relation here. So you know V, you know L, you know B. So basically you know the EMF. Okay. So this is just a direct application of the formula we just derived. So this gives you the value of EMF induced in a wire. It's important to note that here the length, first of all, because in this case, when you have this moving, uh, wire or this conductor, when we are moving it, it's moving in a direction V, which is perpendicular to the magnetic field. Okay, so it does matter. Why? Because when you have this V cross V turn, So if it was at an angle, you would have had a sine theta component that would come in, right? So V cross B, VB sine theta. In the case where theta is 90, like the case here, you would get it as B into B. Okay, so that means if the conductor of length L moves in the magnetic field with constant velocity V, making an angle theta with the magnetic field, okay, and if theta is not 90, basically this is the more general expression that you end up getting. Okay, so BLV sine theta would be the induced EMF in the wire. Okay, now the minus sign that we just discussed. So we wrote that the EMF is given as minus d phi dt. So that hints at the fact that nature abhors a change in flux. So that means the EMF is generated in such a way that it tries to nullify the change that causes it. Okay? The induced current will flow in a direction that the flux it produces tends to cancel the change. And that is called the Lenz's law. Okay. So basically any question where we talk about the direction of induced current, we can bring in this idea that the direction of the induced current would be such that it would try to oppose the change in the flux. Okay, just as the last case when we were discussing about this loop that was moving away from the current carrying wire, we saw that the field was counterclockwise, and we could answer it from the idea that, the flux is reducing. So the magnetic field should be in such a way, the current should be in such a way that the flux, it tries to increase the flux. Okay, so it tries to nullify the change. So based on that, we can try to answer questions like this. So here it says that you have a square loop of some dimensions given. The side is given as A, and there's a non-uniform time-dependent field. So your magnetic field is changing as a function of time. And because the magnetic field is changing as a function of time, that means the flux is changing as a function of time. So that means there is an induced EMF. Okay, we have to find the EMF. So that means we have to find the rate of change of flux. Okay, so in this case, what would happen is the square loop is not moving. Okay, so that means the area is not changing. What is changing is the magnetic field. Okay, so basically you can consider try to find an expression for your flux, where flux is nothing but the surface integral. So B into dx dy, and as you can see, B is a function of y. Okay, so now as you do, the sides are given as of length A, so your x and y both ranges from 0 to A, and then you basically do this surface integral. Okay, and if you do the integral, this is what you get. So this is your expression of phi. Okay, so now we have to find d phi dt. Okay, so as your magnetic field is a function of time, so as you change time, your magnetic field changes. So now if you do d phi dt, so the EMF is minus of d phi dt. So basically this, right? So as you can see, the magnetic flux can change because of changing magnetic field. It can change because of changing area enclosed by the region of the field. Okay. In this case, the area remains constant, but the field varies, and therefore the flux. This is the relation that relates the EMF induced in the loop. There can be all these different kinds of question. So like here, it says that you have a long solenoid of some radius A, and there is this field, which is a sinusoidal field, and now the field is a function of time. As you can see, it has this V naught cos omega t term. So the field is changing with time, and you have a circular loop of a given radius, and the resistance of the loop is also given, and it is placed somewhere inside the coil. So that means it's placed in a region of non-zero magnetic field, and the magnetic field is changing with time, which again tells us that the flux is changing with time. So we have to find the rate of change of flux, and that would give us the EMF. Once we know the EMF, because the resistance is specified, we can actually find the current that is induced. Right? So basically, if your phi, here again you can see the area remains constant. So pi a squared by a by 2 whole square. A by 2 is your radius. So this is your area into B. which is P naught cos omega t for a certain time. Now you want to find the rate of change of flux, basically EMF. So you do a time derivative. So if you do a time derivative, this is what you get. Okay. Now, if this is your EMF, which is basically the potential difference, so you know V, the resistance is specified as R, so you know the current. Okay. So the current as a function of time would be given by this relation here. Okay. So this is how you can, try to find expressions for different kinds of questions where you are asked about the induced current, the direction, and all of that. So one such question in the last year's assignment was something like this, where you have a conducting circular loop of some given radius, which was in the XY plane, and the magnetic field was specified. And the magnetic field, as you can see, is again a function of time, similar to what you have here, right? It's a cosine function, which is a function of time. It's changing with time. Now, what is the induced voltage in the loop? So this is similar to what we have seen before, like similar to the last question. So again, here we know the radius, so we know the area that is enclosed. The field is changing. So from here, if you compare with this question, basically, we can compare this expression to find that 20 is equal to B naught, okay, and 377 is what is omega, right? So now basically you can use this relation in a way to find your, so in this case, your A by 2 is nothing but 20. Okay. So pi into radius square will be your area. And then you have to do dB dt, which will be a time derivative of this term that will, so you can understand there'll be a omega coming out of this, like cos omega t. When you do a time derivative, you get omega sine omega t. Okay. So that when multiplied with the area would give you the rate of change of flux, and that is your induced voltage. Okay, so you can try to solve similar to this. So in this kind of questions, be careful about the units. So here you can see there is this 10 to the power minus 3 coming in because of this. You have the radius in centimeters. So try to be consistent with the units that can otherwise result in an error. Okay. So that's how you can try to solve this question. These are very standard questions, which just makes use of the fact that you have to find the rate of change of magnetic flux. Okay, so now if we look into this relation, which basically comes from this Faraday's experiments. So the Faraday's law tells us that when you have a changing magnetic field, the rate of change of the magnetic field is related to the curl of the electric field by this relation. And then in the last class, we had discussed about Ampere's law, where we had seen that curl of magnetic field is equal to mu naught J. So that means it is telling you that if you have some, current sources, then this constant current sources that you have given by J, that would result in a magnetic field. And if you have a changing magnetic field, that will also result in electric field. So in a way, you can see that there's an analogous form that is coming up between electric field and magnetic fields here. Okay. Now, curl by itself is not enough to define any vector, right? You also need the divergence. So how are the divergence related? So in a way, when you're talking about induced electric field, you so even if consider a region where there is no free charge, okay, but you just have a changing magnetic field. So this electric field that is generated by a changing magnetic field has no contribution from any volume charge density. Okay, so basically rho is 0. So because rho is 0, it's a pure Faraday field. So in that case, the divergence of E is 0. And we know that magnetic monopoles do not exist. So again, for magnetic fields, divergence of B is 0. So now you can find a perfect parallel between the two. So you can say that the Faraday induced electric field, that is the field that is getting generated because of changing magnetic field, okay, which is the Faraday induced electric field, they are determined by minus dB dt in exactly the same way as magnetostatic fields are determined by mu naught J. Okay. And you can also write the same in terms of in the integral form. Okay. writing the same in terms of integral form will tell you that if you know I enclosed, okay, I enclosed by in a region, what is the net current enclosed, that can give you a magnetic field. And similarly, the rate of change of flux would give you the Faraday induced electric field. So again, in this case, you can use the similar ideas of Amperian loop as you had done for the magnetic field calculations in order to find the Faraday induced electric fields. Okay. So now let us try to solve this question where here you have a uniform magnetic field. Okay, so the magnetic field is uniform, pointing straight up. It fills a shaded circular region. Okay, and what is the induced electric field? Okay, so there is a magnetic field and you have this Amperian loop considered, right? You want to find the field somewhere here. So what you can do basically is you can use this relation, right? So you can say, what is the electric field in this region? So you can do a line integral. So consider a Amperian loop, circular loop. So the line integral will be like E into 2 pi s. Okay, so s is your surface integral, like the line integral along this Amperian loop of radius s. And what is the flux linked to this region? So the flux linked is nothing but area into rate of change of magnetic field. Okay, so pi s square, and then you have minus dB dt. So that means this, now if you relate the two, you get a relation between the electric field, the induced electric field, and the changing magnetic field. So this is telling you that if the magnetic field is increasing, okay, E runs clockwise and vice versa. So this can also be understood from Lenz's law, right? So suppose if your magnetic field is increasing, that means the flux is increasing with time. So you want the current in this loop to be in such a direction that it reduces the net flux. So for this, what you have to do is, so consider the case, if you have a current carrying wire, if the direction of the current is clockwise, the field is downwards, right? So that means if you want to reduce the magnetic field that is being the net flux, you have to reduce the magnetic field. So that tells you that the current has to be clockwise when you have an increasing field. On the other end, if you have a decreasing magnetic field, that means the net flux is decreasing with time, then the induced current direction would be reversed, because then your induced current will be such that it would try to increase the flux, okay, and then it would run counterclockwise so that the net field is upwards. So that's how, based on how your magnetic flux is changing, your direction of induced currents would change. Okay. Now, this is a very interesting question, which uh, talks about this case where you have a line charge, okay, along this beam of a will given as lambda of radius b, and it is free to rotate, okay, and then this region, this shaded region, is the point where you have a uniform magnetic field V naught pointing up, okay. Now, as long as your B naught is a constant uniform quantity, that means the flux linked is not changing. So there is no net current here. Nothing is changing. Everything is stationary. Fine. Now, what happens when someone turns the field off? So the moment you see, when you turn the field off and wait for sufficient time, everything goes to zero. Again, there'll be nothing, right? Everything will be stationary. But the transient region where the magnetic field goes from B naught to zero as one turns the field off. So that transient region, there would be a change of flux, right? And the change of flux is basically decreasing flux, right? Your B naught is decreasing with time. It is going from B naught to zero. And so the flux is decreasing. So that decreasing magnetic flux would result in a net EMF that would be generated along this line of charge, right? So that means the charge will start moving because there'll be a potential difference that would be developed. Okay. Now, what will be the direction of this charge? So the direction of this motion of the charge, or the direction of the current, will be such that it would try to increase the magnetic flux. So the charges should move in such a way that the direction of the field should be upwards, right? So that it tries to nullify the decreasing flux. Okay. So basically, this is how your, you know, the induced electric field would be. So the charges will start, there'll be a motion along the rim in a direction which is counterclockwise, right? So that the net magnetic field is upwards, so that it tries to nullify the change of decreasing flux. Okay. So that means an interesting point to note here, as you can see, the region where the charge is moving, which is along this rim of radius b, there is no magnetic field here, right? So it again hints at the fact that you do not require, so it's not the magnetic field that is causing these charges to move. Okay, the work is not done by magnetic field. It's very important to understand that. So this is happening. So even if there is zero magnetic field here, and you know you still get a net EMF or a net potential difference, which results in the flow of charge. And that is coming from the fact that the effective flux linked in this region has changed. You do not require the magnetic field to be present at this point for the EMF to be generated. Okay, it's just the flux linked. If that changes, that results in the change, the induced electric field. Okay. So it's the electric field that is doing the rotating. Okay. So this tells us that, again, that fact that, the magnetic field is always zero at the location of the charge. Okay. So we don't put in any extra external electric field. As we switch off the magnetic field, the flux changes, and that automatically generates the electric field, which rotates the wind. Okay. So till now, these are the relations that we have derived. Okay. So it gives us a relation of divergence and curls of electric and magnetic field and how they're related to the charge density, the current density, and this is the Faraday's law, which again relates the changing magnetic field to the electric field. Now, what was seen is that this by itself is still not complete. Okay. And there was a flaw that was observed in the Ampere's law. So what's the problem? So it was seen that we know that divergence of curl of a vector should go to 0. So if you do divergence of curl of E, this is what you do, and we know that divergence of B is always 0. So this is consistent. But now if you do the same for equation 4, that is Ampere's law, it tells us that for the left hand side to be always 0, your divergence of J should always go to 0. So in magnetostatics, we know that, if you have steady currents, the divergence of J would go to 0. But what if we are in a region which is beyond magnetostatics, right, where things are changing? So there is no reason for us to have the condition of divergence less J always, right? So J can have a non-zero divergence. So in that case, the identity would fail, right? This will not work. So there's something wrong. So this is telling us that the Ampere's law works for magnetostatics, but it's not always correct. So there's something wrong, because this term, the gradient, divergence of curl of B should always go to 0, identity. So so that means something has to be added to this term here, which makes this go to 0, irrespective of whatever J you choose or whatever conditions, right? So that is what Maxwell brought in. Okay. So what said is that we know from continuity relation that divergence of J is nothing but minus del rho del T. And from the first relation, we have a relation which relates rho to the divergence of electric field. So basically, you can say the divergence of J is nothing but minus del T of epsilon naught divergence of E. Okay. So basically, divergence of this term. So now what you can, so this by itself tells us that now if you add, so divergence of J is nothing but minus of this term, right? So if you add this term to your equation, this will basically make the left hand side go to 0 when you take the divergence, right? So that is the extra term that Maxwell added. Okay. Now, but this is very interesting because now if you consider the case where J is 0, okay. So what you end up getting is curl of B equal to mu naught epsilon naught del E del T. So this is again telling you that now a changing electric field can also induce a net magnetic field. Okay. So here the entire picture, like the picture gets connected completely, where in the Faraday's case, we saw that a changing magnetic field produces an electric field. Here again, we see that changing electric fields can also result in a net magnetic field, which is related by the relation here. Okay. This term, this extra term, okay, so if you compare this with J, you would say that this epsilon naught del E del T, this term is also similar to some current term, right? And that is what Maxwell termed it as displacement current, okay, JB. So now that means you can have different kinds of, questions. So suppose in a question where if you know the electric field, okay, and we know how the electric field is changing with time, suppose. That means you know what is the displacement current. Once you know the displacement current, you can actually try to find the magnetic field that this changing electric field generates. Okay. So one of such questions which make use of this relation is here. So this was also a question from last year's assignment, which tells us that you have this 50-volt generator at 10 megahertz. It's connected to the plates of an air dielectric parallel plate capacitor, and the area is given, the separation distance is given, okay, and you have to find the maximum value of displacement current. So in order to find displacement current, okay, so remember this is current density, okay. So to find the net current, you need current density and you need the area. Now area is already specified to you. So basically you have to find the current density, displacement current density, JD. And for that, you need to find the electric field and you need to find how the electric field is changing with time. Now, as you can see in this question, in many cases, the electric field will not be, specified directly. But we know that if we know the potential difference, electric field and potential differences are related to each other. Okay, E is equal to minus grad V. So if you know the potential difference, you can basically try to find the electric field, right? So here in this case, as the question suggests, so you have two plates, okay? Two, yes. So you have two such plates. The potential difference between the two plates is given as 50 volt. So this is the potential difference across. What is the distance? The distance is also specified, right? The distance is 0.1 mm. That is the separation distance. So you know V, you know D. So basically you know the electric field. Okay. So E is equal to V by D. It's nothing but E equal to minus grad V. And what is grad? Del del X and del del Y, del del Z. So here if you do it, this is your dimension of interest. So basically you get V by D. Okay. So once you know V, you know D, you basically know E. Now, important point here is your V is not constant. Your V is changing. It's a generator at 10 megahertz. So basically V is of a form of V naught sine omega t kind of thing, right? Where omega is the it's given in hertz, so omega is nothing but 2 pi into 10 megahertz, like 10 into 10 to the power 6, right? So that means you know omega, that is your angular velocity. Okay, so whenever your for numerical purpose, you should remember that when your frequency is given in hertz, you have to, when you are replacing omega is your angular velocity, so you need to multiply by 2 pi. Okay, so omega is nothing but 2 pi into 10 into 10 to the power 6. That's your changing frequency of your changing voltage. Okay, so now you know. So V is something like, for this case, V is something like 50, okay, into sine, okay, omega t. This is your B. Omega is given as 2 pi into 10 to 10 to the power 6. So now when you have to find electric field is this V by D. D is also specified. Now, what is del E del T? You need to find JD. So you have to do a time derivative. So basically you would get 50 into omega into cos omega t, right? So that would give you the electric field. So because your like potential difference has a sinusoidal dependence, you have to do a time derivative with respect, like, respect to t, and that would give you the changing electric field, and then multiply by epsilon naught. Okay, that gives you the displacement current density. Now for current, so this, the unit here will be per unit area. So if you are asked to find the net displacement current, you have to multiply this by the area. Okay, so displacement current is JD into area. And the area is also specified here. Be careful about the units. So that gives you the value of displacement current. Okay. Okay. So that means now we have all the entire form of this Maxwell's equation. This is the complete set of equations. Okay, so this one came from Gauss's law, this one from the fact that there are no magnetic monopoles. This is our Faraday's law. And here the first part was from the Ampere's law, and then you had this Maxwell's correction coming in, which brought in the factor of displacement current. So if you look at it, you can see that the electric field and magnetic field are now, coupled and relative to each other. Okay. Now, these four equations that we just derived and discussed lie at the heart of how electromagnetic waves work, or electricity and magnetic fields are connected to each other. So now if we talk about electromagnetic waves in vacuum, we can consider the case, first of all, what is a wave? So a wave is some function which changes with position and time. Okay. So in 1D, if you have some wave which is given by this function f, it's a function of z and t, where z is your position, like the spatial coordinate, t is the temporal coordinate, then it satisfies this relation, which is this Helmholtz relation, which has this form. Okay, so now here v is the velocity with which the wave propagates. Okay, and basically when you have this form, you can consider, suppose if you consider some what do I say, some sinusoidal function. Okay, so if you consider f to be something like a cos kz minus omega t, with some phase term delta, so there are two dependencies, right? One is a temporal variation, one is a spatial variation. So there can be temporal periodicity, there can be spatial periodicity. So the omega t term takes care of the temporal change, right? So where omega is your uh, angular frequency, which talks about how it changes as a function of time. So you can define time period as 2 pi by omega, right? On the other hand, you have a spatial variation, which is given by the wavelength. Okay, so this term here, kz, talks about the direction in which your wave is propagating. Okay, so for this part, it is propagating along z. In a more general form, you would have something like k dot r. Okay, so here you would have something like k dot r. Okay, so which is the most general form, where k gives you the direction of propagation of the wave. Okay, and 2 pi by k is basically lambda, which defines your wavelength, which gives the spatial periodicity of the wave. Okay, so now you can, like, this is a general form of how you can have a periodic wave given by this relation, and how the temporal and the spatial periodicities are defined. Now, if we look back, if we go back to the Maxwell's equation, okay, and consider the case where they, so that basically rho and j goes to 0. So you have a form like this. This is basically coming from this relation, right? All the four, putting rho and j to 0. So as you can see that electric field and magnetic field are coupled to each other. Okay, so you can try to decouple them by doing this vector algebra. Okay, so curl of E. So you can use this identity and from here get this relation. Okay, so here when you get curl of B, you use this relation, curl of B from here. Similarly, you can do curl of B and then put divergence of B to 0. Here you have put divergence of E to 0. So basically you end up getting these two relations, right? So now you can see E and B are decoupled and they have a form similar to what you had here, right? So that means in vacuum, you can see that where there is no charge or no current, rho and j are 0, electric field and magnetic field satisfies the three-dimensional wave equation. So important to note it's three-dimensional because electric field and magnetic field, both of them are vectors. So you have, this tells you that you have similar expressions for all the three components, Ex, Ey, Ez. Okay, so it's a three-dimensional wave equation. And if you compare this with this relation here, you see that the velocity of the wave, okay, is given as the speed of light. Okay, so this explained or validated that the light is an electromagnetic wave. So light, when there is a propagation of light, is basically nothing but propagating electric and magnetic fields. Okay, propagating with this speed in vacuum. If you have some other medium, then this speed would change, right? And that is something which we already know, that how light changes, the speed of light changes as it goes in different medium. Basically, that defines the you can say the refractive index of the medium. So all these ideas are already known to us, but basically this defines the wave equation that governs propagating electromagnetic waves in vacuum. Okay. So now if we again look back at what this is telling you. So divergence of E goes to 0, divergence of B goes to 0. This is telling us that propagation of the wave. So if you have a wave propagating, there is electric field and magnetic field, which is changing with time. Now this electric field and magnetic field, the direction of the fields are perpendicular to the direction of propagation of the wave. That's why electromagnetic waves are called transverse waves, and that comes in from here. As you can see, if you have a wave propagating along Z, the Z components go to 0 because divergence of E and divergence of B, both of them are 0. Okay. Now, again, from Faraday's law, by using this relation, you can actually find a relation between electric field and magnetic field. So when you have a light, you know, light is composed of electric field and magnetic fields. And as we just saw, so if you have a light propagating in a direction given by the k vector, okay, the electric field and magnetic field are perpendicular to it, and they are not unrelated to each other. E and B are related to each other by this relation. Okay, so if you consider the electric field to be, something of the form k z minus omega t, and similarly the magnetic field with something like some uh, special like k dot r term and some omega term, then when you do a time derivative with respect to like del b del t, you have omega t term in the magnetic field, right? So that will give you a omega. And when you do curl of E, this is a derivative in the spatial coordinates, right? So you would get a k out. So basically, this is how the component wise, this is how the electric field and the magnetic fields are related to each other. So in a more compact way, this is what this is telling you. So that means if you know the direction of propagation of your wave, if you know the electric field, you can basically use this relation to find the magnetic field. And the electric field and magnetic field are perpendicular to each other, mutually perpendicular, and they're also perpendicular to the direction of propagation, that is the k vector. Okay, the amplitudes, as you can see, are related by this relation here. So if you want to find, as the electromagnetic field is propagating, what is the energy per unit volume? Okay, so this is your contribution from the electric field, this is the contribution from the magnetic field. But now if you use this relation of how electric and magnetic fields are related to each other, you would see that they're related by this relation, right? So the electric and the magnetic contributions to the energy are equal. Basically, the energy per unit volume can be just given as epsilon naught E square. Remember, this is in vacuum, still in vacuum, okay? So as the wave travels, it carries the energy with it. So if you want to find the energy flux density, it should be in a direction perpendicular to both E and B, right? It should be in the direction of propagation of your wave, and it's given by this relation here. So this vector is called the Poynting vector, which gives us the energy flux density. Okay, so for a monochromatic plane wave propagating in the z direction, so that's why you have this kz term with some frequency omega. Okay, this is how your Poynting vector will look like. So you can see the wave is propagating in z direction. The Poynting vector is also in the z direction. Okay. Okay. So that's about the fundamentals of electromagnetic waves propagating in vacuum and how how the equations come from, starting from the Maxwell's equations. Okay. Now, based on what we have just discussed, we can try to solve different kinds of numericals. So one such question is here. So consider a solenoid of some radius r with n turns per unit length. Okay, so you have a time dependent current. So in a solenoid, if you remember, there are many turns. Okay, current carrying wires wound around, making multiple turns. And because you have this current flowing through them, there's a net magnetic field that gets generated, right? So if you have a constant current, the magnetic field inside is given as mu naught Ni, right? So now if you have a constant current, you have a constant magnetic field. In this case, your current is a sinusoidal function. So that means your magnetic field will also be varying with time. Now, because the magnetic field is varying, that means the flux linked to the coil is varying. So it is asked that what is the magnitude of electric field at some perpendicular distance, some like r less than r, so somewhere inside the solenoid. So basically you have a solenoid like this. Okay, you have current flowing through it, the current is fluctuating, that means the flux linked is fluctuating. So somewhere here in this region, somewhere inside, what is the magnitude of electric field? Okay, that's what is asked in the question. So as you can understand, you can consider any region. Okay, so the area will not be changing. Okay, basically what is changing is the current. So the magnetic field is basically changing. Okay, so it's the rate of change of magnetic field that is changing the flux. So you can consider something like this. So the magnetic field is given as mu0 Ni, but now your current is a function of time. Okay, and you can do an integral. Basically, if you take a small circular loop, of some radius r, okay, so the area would be pi r square, and because your magnetic field is changing, you have this di dt coming in, rate of change of current, which is causing the magnetic field to change. So you have this omega cos omega t term, and the magnitude of this is what is the magnitude of the induced electric field. Okay, so if it was asked somewhere outside, then as you can understand, the field outside is zero. So the induced electric field is inside the solenoid. Okay. So there can also be questions like this where you have the electric field of an electromagnetic wave. So the electric field is specified. You want to find the magnetic field. So just few slides back, we discussed that the electric field and the magnetic field are related to each other by this relation. So for any wave, if you know the propagation direction or the k vector, if you know the angular frequency, if you know the electric field, you can use this relation to find the magnetic field. So in the question, this is how the electric field is specified. Now this expression by itself has the information of k and it has the information of omega. How? So we know that omega is the temporal variation, right? So if you compare this temporal term, this is nothing but omega t term, right? And again here, so 1000 into pi, that is basically your omega. And here, so in the most general case, we know that the spatial part is given as k dot r, which is nothing but kx into x plus ky into y plus kz into z. So here it is telling you that your kx, if you compare, you would get that the kx is given as 0.3 pi, ky is given as 0.4 pi, kz is 0, right? So that means you know k, the k vector, which is kx I cap plus ky j cap plus kz k cap, right? So if you know kx, ky, kz, you know k, the k vector. So you know k, you know omega, you know the expression of electric field. So now you can find the magnetic field. Okay. So it's like this. So if you compare, your k vector turns out to be this, your omega turns out to be this. So now you can use this relation to find the magnetic field. Okay, so in all these kinds of questions, there can be several such questions where electric field is given, you need to find the magnetic field, or the magnetic field is given, you need to find the electric field, or suppose E and B both are given, the Poynting vector is asked. Okay, so then you have to go back and use this relation, right? So if you know both E and B, you can basically try to find S. Or suppose as in this question, if S was asked, so in that case, you know E from here. You use all the relations, okay, all these relations to find B. Now, if you know both B and E, you can then find S, right? So all this kind of questions can come up. So in this case, the answer would be given by this relation here. Now, transformers work on this idea of induced currents. So basically, you have some primary coil where the current flows. It's a alternating changing current. Now, when the current in the coil changes, it's the magnetic field that it produces changes. So now if you have a second coil, which is the secondary coil, then the flux, magnetic flux linked to this secondary coil changes as the magnetic field changes. Okay. So the current change in the primary coil results in the change of magnetic flux linked to the secondary coil, and that results in a net current in the secondary coil. Okay, so that's the basic idea of transformers. So based on that, here what you see is this question where it says that there is a primary coil where the current IP flows, and this is how the IP flows. IP is as a function of time. Now it is asked that how will the current in the secondary coil look like? Okay, so how do we find that? So we know the current IP. Okay, now if we just try to write it mathematically, what we just discussed. So if IP changes with time, IP is a function of time, right? So if IP changes with time, then the magnetic field changes with time, right? The magnetic field that it generates. Now, if the magnetic field changes with time, that results in flux change. So basically, the flux change. So if we have to find d phi dt, right? D phi dt is what is resulting in the secondary current, right? That results in the EMF, which results in secondary current. So d phi dt is coming because of the changing primary current. So in a way, d phi dt is associated with, or you can write it as is related to something into minus of di dt, right? So it's at least you can, oh, sorry. So at least you can write it as something like proportional to, this is proportional to di primary dt. Ignore the spikes, dt. So basically what you have to then find is the rate of change of, uh, and there's a minus sign, right? EMF is minus of d phi dt. So basically you have a minus here. So d phi dt is proportional to this, and the EMF is basically, so EMF, which is again, so E by R would be your current, right? So the variation of the EMF will determine the variation of the secondary current. So this is proportional to minus of di dt. So that means by now, by looking at how the primary current is changing as a function of time, in this section, what is your di dt? As you can see, it's a straight line. So that means the slope is constant. So di dt is a constant quantity, right? Here, the current is not changing. So that means di dt is zero. Again, here it's a constant quantity, but it's a negative quantity. Now, because your EMF is minus of d phi dt, so it's proportional to minus of di p dt. So that means, as you can see, out of all the options, this is the correct one, right? So here you have a constant secondary current. Here the current goes to zero because there is no slope here. And then again, here is a constant positive value because Is is proportional to minus of d dt of Ip. Okay. So all this, simple questions, but conceptual ones can come up, which makes use of the fact of the induced electric fields. Okay, magnetic induction. So this is it, right? So C is your answer. Now there can also be questions like this. So here it says that you have a magnetic field Bz in a region x greater than 0 and 0 everywhere else. Okay. Now a rectangular loop in the xy plane of sides L and H are given. Okay, so you know the dimensions of your loop and is inserted into the x greater than 0 region from the minus x less than 0 region. So basically you are moving towards the magnetic field region. Okay, so you have a uh, region where you have a magnetic field, okay, and you have a loop. So somewhere in somewhere below, and then you are taking it in the region of the magnetic field with some velocity v. Okay, so the velocity is not along this direction, sorry. The velocity, so this is your region. The magnetic field is along z. Okay, so you have a net magnetic field. Now, basically you have a loop somewhere here in the negative, like below in this region, and you are taking it towards, okay, z less than 0. I'm not drawing it properly. Something like this, right? Yeah, now it looks fine. So x, y, z, you have a magnetic field in the z direction. You have this loop, and you are taking it from z less than 0 region to z greater than 0 region where the magnetic field is present. Okay, so you have some magnetic field in this region with some velocity v. So that means this governs. So now, because you're bringing the loop into the region of magnetic field, so this velocity governs the rate of change of flux, right? And this is the direction in which you're bringing it. It's along x. Now the question says, which of the following values of L and H will generate the largest EMF? Okay. So for this question, we have to again go back to our idea of motional EMF. So if you go back to the idea of motional EMF, what we saw is that, let us go back and see what it is. what it told us, right? Uh, Somewhere here. So here, so here what you saw, it's similar to this question. Where is my marker gone? So it's similar to this, right? So here what we saw is, again, here it was the loop that was being moved and that was resulting in a net magnetic flux change. Right? Now what we saw is that in whatever direction we are moving, okay, the net force that gets generated is in a direction perpendicular to the magnetic field and to the direction of motion. So when we were moving in this direction, the direction of the force was in this direction, right? Along. So if this is x, then this was along y. The force was along y, right? So it was perpendicular to the direction of the velocity, right? And when we finally solved it, we saw that the EMF generated is proportional to dimension. Okay? The dimension along the force, or you can say the dimension perpendicular to the velocity. Okay. So now if we use the same concept, basically you're trying to increase the flux, right? So one dimension, the area that contributes in the flux, one of the dimension is along V and another dimension is perpendicular to V. So the dimension along V, the rate is governed by the velocity itself. So the other dimension, which is perpendicular to the velocity, is what contributes to the flux value, right? So that means if you have to increase the flux linked, okay, or if you have to increase the EMF or the rate of change of flux, basically you have to increase this dimension, which is along the direction of the induced force, or you can say along the direction or perpendicular to the direction of the velocity, okay, and also perpendicular to B. Okay, so now if I go back to the question that we were discussing, so here the motion B is along X, okay, the magnetic field is along Z. So what is the dimension that is perpendicular to V and B? That should be along Y, right? So as for the diagram and also in the question, you can see H is along Y. So that means if H is maximized, the EMF will get maximized. So now you can look at all the options and see which combination results gives us the maximum value of H. L does not matter, right? Because in this direction, it's the velocity that controls the flux change. While in the perpendicular dimension direction, like in this case, it's this dimension that contributes to the flux change or the EMF. So out of all the options, you can see the second one has the largest value of H. So the largest value of H contributes or results in the largest EMF. Okay. So these are very simple yet a little, you know, questions which make use of the concepts that we had been discussing. So phi, the magnetic flux is proportional to BHX. So basically H matters. Okay. So the answer here is B. The H is the dimension which is perpendicular to both the velocity direction as well as the field direction. Okay. Now, this is a very, standard, but you can say conceptual question. So it says that, if you have a metallic wire coil and it's stationary in a non-uniform magnetic field, what is the EMF induced in the coil? So in this kind of questions, you have to be careful about, and be cautious basically. So the coil is stationary. Okay. So you can say that the area is not changing. Okay. Now, what can result in the induced EMF? For induced EMF, we need a changing flux. So that means if the area is constant, the magnetic field has to change, and it has to change as a function of time. Okay. So in this case, when you have a non-uniform magnetic field, in a very first, just by looking at it, you would say that, okay, it's non-uniform, so that would result in a magnetic field. That's not induced EMF. That's not the case, right? So what it is telling you is, if you have some coil, okay, and it's stationary, and there is, suppose, B1 field here, and suppose B2 field here, okay. So the field is non-uniform in this two region. But if this non-uniformity is not changing with time, then the net flux that is linked to this coil is not changing with time. So field being non-uniform does not mean that the field is changing with time. Be careful about this fact that when you talk about, changes in field, whether it's changing as a function of position or as a function of time. So here the field is non-uniform, but it's not temporally changing. So if it is not changing temporally, then the net flux linked to the coil is not changing with time. So then there is no reason for any induced EMF. Okay. So in this case, you would have the net induced EMF to be 0. Okay. Now, again, there can be questions like this. So here it says, there is one of the questions from the last year's assignment, which says that you have a uniform magnetic flux. This is my marker. So you have a uniform magnetic flux. So B is uniform. It's present in the entire space. So B is not changing. And then you have some conducting loop with some dimensions given. Okay. And it's kept in the plane. So basically you have a region, the entire region has a magnetic field, and you have a loop. The loop dimensions are fixed. So the area is not changing and the magnetic field is not changing. So that means there is no change of any flux anywhere. Okay. So because there is no change of flux, that anyway tells you that there should not be any induced EMF. So the net induced EMF should go to 0. So for any kind of induced electric field, Faraday induced field, you need to have changes in the magnetic flux. Okay. So in this case, the answer would be C. Okay. Now, there can also be questions like this. So as you can see here, so it's a uh, conducting circular loop with the area given is placed perpendicular to the magnetic field. So the area is perpendicular to the magnetic field and the magnetic field is specified. Okay, that is my pointer. So the magnetic field is specified. You can see that the magnetic field has a temporal dependence. Okay, the area is specified. So you basically know how the flux is changing because you know how the magnetic field is changing. Okay. Now find the charge flowing through any cross section during time t equal to 0 to some time 40 millisecond. Okay. Now, if the resistance in the loop is given, find the thermal energy that is developed. So let us look into the question one by one. So what all are given? So the area is given. In order to find flux, we need magnetic field and area. Magnetic field is also given. In the expression of the magnetic field, what do we see? So there is omega that is given, right? Omega is 50 pi given. The B naught value is given, which is the amplitude of the magnetic field. Okay. If omega is given, that is telling you the time period, right? Temporal change. So 2 pi by omega is equal to the time period of your uh, thing. So from here, you can actually find the time period of your magnetic field. Okay. So now if you try to find the time period, what do you get? Okay, so try to find the time period first. B naught is already given, the area is given. You know how B is changing with time, so basically you know phi. So 1 second. So you know phi, and you also know d phi dt, right? Basically, you know the EMF. So if you know the EMF and then if you know the resistance, you know the current. You know current, you know R, you know the joule. From Joule's heating, we know what is the heat that is generated, right? That's I square R. So basically, you then know the thermal energy. So that's how you can try to answer this kind of question. Okay. So like here, this is all are what is provided. So you can write the flux as V naught A sine omega t. The induced EMF is minus d phi dt, is minus A omega cos omega t. The current is EMF by R, which is B naught A omega pi R minus cos omega t. So now if you put in all the values, what do you see? So 2 pi by omega, this gives you the time period. Okay. So now the first part of the question says find the charge flowing through any cross section during the time t equal to 0 to 40 milliseconds. So this 40 millisecond is nothing but the time period. So basically you have to find the charge flowing through the loop in one time period. So if you know the current IDT from 0 to capital T, the time period will be your charge that is flowing in 40 milliseconds, right? So now you know the expression of I. This is your expression of I. So you put in here, and as you can expect, the net current goes to 0 because you are trying to find the net charge, not net current, net charge that is flowing through the loop in one time period. So that goes to 0. Now, how do you find the thermal energy? It's nothing but I square R. And you want to find the net thermal energy in this time period. So you do a time integral from 0 to t. So I square R into dt. That's the energy. Okay. So let's do this integral. So here it will be a non-zero quantity because you have cos square omega t. Okay. And this is just integration. You put in the values that you already know. Pi is a constant. So B naught A omega and R. And this gives you the answer. So in all these kind of questions, be careful about the units. Okay. So there can be all these various questions which make use of the fact that, so if you know the magnetic field, you can, or the area and how things are changing with time, you can find the flux, the change of flux, therefore the potential difference. If you know the resistance, you can find current, you can find the Joule heating and all of it. Okay. Now, there can be questions like this. So as you can see, these are some questions from last year's assignment. So here you can see that it's a circular coil of some, uh, magnetic flux, which is given by this relation here for each turn. Okay. So each turn of the coil, this is how the magnetic flux is. Okay. And in t seconds, what is the induced EMF? So if you know the magnetic flux, okay, and you know, so for each turn, this is the case. For n turns, so if for one turn the flux is phi, for n turns the flux is n into phi, right? So now it is said that the induced EMF for t equal to is minus 1 volt. So what is the number of turns? So what you can do, you know how your basically your B is now a function of time, right? So your B is a function of time. Okay. The area can be some constant. Okay. Uh, okay. Now for each turns, so now then, okay, this is the magnetic flux basically. So this already has taken care of the area, right? It's the magnetic flux through one coil. So A into B goes by this relation. So basically what you know is phi for one coil, right? Now, what is the phi for N coil? It should be N. So basically, what you have to do is N, which is your now, if the number of coil turns is N, then N into phi for one coil. That's your net flux. Okay. Now, this is a function of time, okay, which is given here. The function is given here. So now if you find epsilon is like the EMF is nothing but minus d phi dt, right? So that means d dt of, so what you can say is N into d dt, that is, I'm not trying to write, okay, so it's like problematic. This, I'll try to write the minimum possible. So basically N into N into d dt, which is the derivative of phi 1, okay, that this value, the rate of change of flux, okay, so I'll ignore writing, I'll just tell, okay. So you know the flux for one coil, so the flux for N coil will be N into this value, right? And N into minus d phi dt, okay, so N into derivative of this equation for t equal to 16 is known, that is minus 1. So that means if you know the derivative of this function, you put in the value of t equal to t equal to 16 and equate N into d phi dt at N into minus of d phi dt, where phi is given by this function, equate it to minus 1, and then find the value of N, right? That's your question. You know the flux for one coil. The flux for N coils will be N into that. The flux is a function of time. So d pi dt will give you the rate of change of flux. Okay. And from there, compare it with the given value that you have for a known t, and then find N. That's the answer. Okay. That's how this has to be solved. Now, another question, similar question in the assignment was like, now the number of turns are given. You have a loop wire with 50 turns that is given. The resistance is given. Okay. And the magnetic flux. Okay. Initially, the flux was this. And then the magnet is moved towards the coil and the flux has become this in a time period of 0.21 seconds. So basically, you know the initial flux, you know the final flux, and you know the time of change of flux. So that means you know the rate of change of flux, right? So final flux minus initial flux divided by, once again. So final flux minus initial flux divided by the time of change of flux will give you the rate of change of flux. Okay. Now, what is the induced? It is asking. So you know the rate of change of flux, and you know there are 50 turns. Okay. So if you know the rate of change of flux, you know the number of turns, you can just multiply it to find the net voltage. Now that is your EMF. For that, you don't need this resistance yet, right? You just need rate of change of flux into number of turns gives you the net EMF. So now once you find the EMF, so you know the potential. Now if you're asked what is the current, then you use the resistance that is given here. If you know V, then you can find I as well. There is the rate of flux into N, that gives you the net EMF. And then once you know the EMF and the resistance, you can try to find the current. Okay, so all these kinds of questions can be solved based on the same idea. Now, an important point, or you can say important phenomenon that is associated with this magnetic induction is eddy currents. Okay, so what we saw is that when you have a conductor close to some region of changing magnetic field, there will be currents that will be induced. Now, so if you have a region where, some plate, and then the flux linked to it is changing, then there'll be the magnetic field line, the electric field lines that, or the induced electric fields that would be generated, or electric currents that would be generated, will form loops, okay, closed loops within the conductor, okay, in a plane perpendicular to the magnetic field, and that is called the eddy current, okay, and it has a lot of applications. Uh, so that, and one very well known application is the induction, like induction heating, induction cooking, right? You have this induction oven where we know that, this is how an induction oven looks like, right? So basically what happens here is, how is the heating happening? So here basically what happens is, inside this oven here you have a circular coil like this, okay, and then the current through the coil is changing, which results in a changing magnetic field, okay. Now when you change the when the magnetic field is changing, so now if you put imagine a in this region of changing magnetic field, if you put a region of some plate, some metal plate, okay, then the flux link through this metal plate is changing, right? Now, because the flux link through this metal plate is changing, there'll be currents that will be formed in this region, okay, and then this currents will be basically, this will be, what do I say? Well, 1 second. So you will have currents in loops all throughout this metal plate. And this current basically didn't, so this currents, as we know, current can result in, from Joule heating, we know that current can result in heat. So that would result in a net heating of the plate. So when you have this surface, okay, and you have this changing magnetic field generated from the changing current in the circular coil, and you put a metal plate there, the metal plate gets heated up because of small closed current loops that are formed inside, that are induced inside the metal plate, okay. So that's how things get heated up, and that's how you can have cooking. Okay, you can cook in induction oven. Now, another demonstration of eddy current could come up in magnetic levitation, where you have, so here, suppose this is your electromagnet, okay, and then when you switch it on, that means this is changing electric current, changing current here, that would result in a changing magnetic field, okay. So basically this, so this is showing your changing magnetic field, okay. Now, because the magnetic field is changing, now if you put some, conducting coil here, what would happen? Because of the changing magnetic field, the flux linked to this, like the circular thing that you see here, right? So the flux linked to this circular ring will change, okay. And then what happens is a current is induced in the ring, okay. So now this behaves as a magnet in itself, okay. So now it results in a magnetic field around itself, because you have a current flowing through this, so that current results in a net magnetic field. Now, if the fields are sufficient enough, there'll be repulsion between the two, okay, and that comes from the Lenz's law, if you remember. So they repel each other, and that's the reason why when you have this electromagnet switched on, they repel each other, and that's how you have this levitation. This thing is levitated at this height. Now, if you switch it off, what would happen is this would come down. Okay. So this similar concepts have been used in, maglevs and like, which work on magnetic levitation. So there can be several applications. but it works on this concept of magnetic induction. Now, there can also be one very important application is in, uh, electromagnetic brakes. Okay, so here what happens is if you have a moving disk, suppose, okay, some metal, consider maybe some uh, some metal which is not attracted to the magnet. Okay, so it can be something like aluminum. Okay, now you have this moving disk here, and as it is moving, you have this magnet kept. Okay, so when it moves, what happens in this region? The magnetic flux is changing. Now, because of the Lenz's law would result in some, uh, you know, induced current here, which would try to reduce the change in flux. And because of that, the net motion gets impeded. Okay, so what you will see is that you have this spinning disk. Now, if you bring the magnet here, okay, because of the changing magnetic field as the disk rotates, you would see that the disk motion will get reduced. And this is the concept that comes up as an application in uh, AD brakes or electromagnetic brakes, okay, which works on the same idea of how Lenz's law and induced currents are used when you have conductors in presence of changing magnetic fields. Okay, so there can be all these different kinds of applications of magnetic induction, and uh, that's about today's class. So yeah, thank you. So let's call it a day. Okay, thank you.